Now, it is atomic, molecular, and laser physics. It is a 4 credit course, and the first one is purely based on atomic physics. First grade, you are unit 1. Second one is molecular physics. In third one, there are spectroscopic techniques. The fourth one, which is last, is a laser physics course. This is broad overview of your syllabus, what it is in this semester for this course. So it's a 4 credit course with atomic physics first one, and second one is molecular, third one is actually spectroscopic techniques. I will clear it, check it once again. Actually, syllabus, your syllabus. Which was syllabus, guys? Have you seen the syllabus? Anybody of you? So if not, let me check it. It is atomic molecular. Yes, here it is. Sorry. Yeah, for second unit is as well atomic. Sorry, this one. This is as well atomic part with various and molecular physics. Molecular plus spectroscopic techniques. Plus spectroscopic techniques. Yes, there are then in first unit there is structure, basic experiments regarding atomic structure, and the effects of external parameters on the atom. Then in the second unit there are the advanced features like spin orbit interaction, relativistic correction, lamp shift, fine structure, hyperfine structure, Zeeman effect, all these Brit scheme. Then there's land interval rules, spectroscopic notations, which is important from the examination point of view, that unit. Somebody has written on the screen, so he can erase it. In the third one, it is purely molecular as well as some spectroscopic techniques. Fourth one is lengthy and important, it is laser physics course. We will start from the first unit, which is atomic physics, or unit 1, which is atomic structure and atomic spectra actually. Somebody turn off the mic, please. So, unit 1. Unit 1. So unit 1 is basically about atomic physics actually. Atomic physics means that we will study about it is structure and the various ways in which we can investigate the atomic structure. Like there is one of the Stirling-Rutledge experiment, behavior of magnetic dipole in an external magnetic field, space quantization of atom. These are all important actually from the structure point of view, atomic structure point of view. There is first Bohr model of atom, which was a basic first currently accepted scientific model, first initial, and it gave the current picture of the model. Then quantum mechanical numbers, quantum states of an electron. So all this we will discuss in this unit. Today's lecture is an introduction, and I will not go into the details of any topic today, but I will give a brief introduction with some sort of history. History means that how we came to the present view of the atom. That means the structure which we see today of atom, and whatever the various progresses or the steps which lead to the current structure of atom. First of all, you should remember that atomic physics is incomplete without knowing any property of the atom or the atomic structure. And atomic structure has been revealed through experimental techniques or experimental ways, and those techniques were mainly spectroscopic techniques. That means the atomic spectra and atomic structure, they both are related. We cannot separate them. And it is important to know about the spectra which is produced by atoms under different conditions, and correspondingly we can be able to understand that structure of the atom. For example, if I give an example, simple example, the uh, what is spectra? First, you should remember that what the spectra is actually. So what the spectroscopy is. So spectroscopy actually is both studied in chemistry as well as physics, but the basic principle is same. In this, the spectroscopy actually deals with the interaction of the radiation. Simple. The interaction of the radiation or the interpretation of the radiation. Interaction of the radiation means interaction of the external radiation. That means when an external radiation is struck upon an atom or an material, then this atom will undergo different processes, which we will study later on in another unit or in this chapter. After that interaction, for example, if this is an atom and there is an radiation, and we have something in the output because we are giving some energy, an atom will interact with this energy. And how we will know that it has interacted, what changes are there? They can be observed by different phenomena. One of them is the radiative transitions. In radiative transitions, when the energy is emitted, if we suppose that it has h nu dash energy, if we suppose in some cases when nu is nu dash, it becomes elastic. That is one of the possibility. Nu can be different from the nu dash, or nu can be less than, nu can be greater than. That depends what type of process is going on. So for example, if we assume that it is elastic one, that means the incident frequency is equal to the output frequency. So we have to understand how this incident radiation will interact with atom. What is the nature of the incident radiation? What is the nature of the interaction which is going inside the atom? So when we will know about it, we will can guess some of its properties. One of the examples, you know that, for example, if we have a simple atom in an external optical field, in a simple optical field, external optical field. So in optical field, what we have the, from the modern theory or the current picture, we have photons which are quantized, which have discrete energy, and that much of energy if we give to the whole atom, this energy will match, that means the incoming energy will match some of the energy levels of the atom. When it matches, it can make a transition of the electron from one state to another state. So it can excite an atom from its ground state to some higher excited state, and when it comes back to ground state, it will emit the energy in that same frequency range, unless there is some scattering of that this outcoming photon by some another atom. We are taking into concentration an isolated atom which does not interact with any other, which does not have any neighborhood, such that the, I will draw the diagram here. For example, These are the energy levels of an atom. This is the ground state, or this is the for n equal to 0 or n equal to 1, and it goes to some excited state here. So, so when it goes, because electron is excited by this h nu, it will go here, a vacancy is created, and since it is an excited state, its time duration is 10 is power minus I think 13 seconds something, as we know. I mean, for an ideal case, after this time duration, it will come back to the ground state, because it has to attain its minimum possible energy state, and the absorbed energy will be emitted in the same frequency range. So this type of, that means when we study this frequency distribution versus the energy or versus any property of the atom, it becomes spectra. We have a spectral distribution. Then we have a distribution of frequencies, or distribution of energies, or distribution of wavelength. Wherever there is a distribution of frequency, wavelength, or energy, and we plot this distribution with some particular quantity, like incident intensity or absorption, and then this type of feature is called as a spectra actually. This plotting of frequency distribution or wavelength distribution or energy distribution with respect to a particular parameter, physical parameter, it is called as spectra. And from this example, we can say that when it goes to some ground state, the energy is emitted. And this energy is also discrete. This is not continuous. So one guess we can say that atom has some discrete energy levels which can absorb the energy and then emit. So this is one of the guess we can make, one of the explanations we can go. So in this way, there are a lot of ways, a lot of observations on the experiments which have been going through from various times, from various decades, and then we have to reach to the current form structure which we know of the atom. So if we go a bit back and start from the beginning, where from this concept came, the current form of atom, which we assume it only that it is spherical, but it is not. It has some that so a elongated shape along some edges or the elliptical paths. This is just that probability, which is the current form. But we assume that for timing, if it is sphere, so and it has an central part which is hard nucleus, then it has outer probabilistic ways or paths which we call as orbitals or orbits where electrons can be found. And if we start from this, all started from actually from the basic concept first, that in the ancient times means how ancient I am talking about. I'm talking about from 500 to 428 BC, then 484, no, almost to 370 BC. From 370 to 500, I am talking about in this range. So it is the ancient times. In these times, what was speculations about the matter? The speculations were that matter has a continuous nature, and when matter has a continuous nature, from time to time, its discrete nature was revealed. But at this stage of time, Greek philosophers, they showed that the matter has a continuous nature, and these were argued actually. This the continuous nature of the atom was argued, or the whole matter, or the universe, in the universe, the matter. It was argued that on the basis that universe consists of an empty space, because they were not able to see or observe the air and the various mixture of gases in it at that time. So they thought that universe consists of empty space and of invisible some particles. So here came the concept of particles then, and they thought that some invisible particles are there, which we call them atoms, which differ from each other. So according to them, at the ancient time, at the initial stage, it has been argued that the matter was a continuous, and there were some this empty space in the universe. There are some invisible particles within this space, which later were called as atoms, And these atoms or these particles which were in the space, they different from each other. They differ from each other. And when they differ from each other in the form, so differ in form, they differ in position and arrangement. So it was an early thought. So after this, a lot of time passed and people started to investigate. They investigated theoretically. They make some theories, and when they make some theories, then came the era which was called as modern time. Modern time means from 15th century onwards. So from 15th century, from 15th century onwards, the chemistry played a role actually. In how chemistry played actually role, it played role by discovery of the gas laws. So here the gas laws were into picture because we know that gases have gas molecules which are randomly moving and they give us a picture of particles. So the concept started from here. So people think of that from gas laws, they got the basic, some simple idea about the matter and its discrete nature. And the gas laws which were discussed, like we have Boyle's law in 1662. It is interpretation actually of kinetic theory of gases was there. This was from first Bernoulli in 1738. So I am moving forward now. I am giving the most recent, these are actually the recent as compared to that earlier stage. And this Boyle's law, which were the gas laws actually at that Charles law was there. And then kinetic theory of gases was one of the important contribution in giving the concept of the discrete nature of matter. Then these were modified actually, modified gas laws. I will not go into the details what the gas laws were, what were the modifications were done to them. I'll just give you an idea about how the concept of the Fokker current structure of atom came into existence. So modified gas laws which were modified and developed by actually or classes, J.C. Maxwell, L. Boltzmann, you all know them from the textbooks. Or Boltzmann, they were explained the physical properties of gases actually. So they determined some physical properties of the gases. For example, what they said, I will give you a hint from this. Uh, for example, when they modified the kinetic theory of gases, and from kinetic theory of gases, it was concluded that gases consist of large number of particles called molecules. So the concept of molecules came from the kinetic theory of gases, and it was more this kinetic theory of gases by modifying they came to these conclusions actually. So they consist of the large number of molecules which make elastic collisions with each other and with the walls of the container. You all know from the BSc classes, if somebody has taught this as a subject chemistry in the BSc classes. and with each other and with the walls of container. And this means the gas molecules which make elastic collisions with each other in the wall and with the walls of container. The molecules of a particular substance are all identical. This was another conclusion which was drawn from the kinetic theory of gases. Walls of the molecules of a particular substance are all identical and are small compared with the distances between them. What does that mean? That means if we have a container, we have a gases in this container. So the molecules of a particular substance, if this is a substance homogeneous mixture of the gases which form a particular substance, they are all identical and are small. That means the size of these particles is small as compared to the this distance between them. This and this was another conclusion. So these are small in entities, these are small structures, these molecules as compared to the distances. The third important property was that the third important property was the temperature of the gas. The temperature of the gas is proportional to the average kinetic energy of the molecules. That is how we got the definition of the kinetic energy, that is average thermal temperature. The temperature of the gas is proportional to the average kinetic energy. So T is proportional to average kinetic energy. That means as the molecules collide with each other, there is the loss of their kinetic energies, how much they fast move, how fast they collide, they lose some energy, and that energy lost in the form of temperature and heat. These were some basic conclusions where the concept of the particles or the molecules or the discrete nature of the matter came into picture. So along with this kinetic theory of gases, there were other laws in chemistry which were going on. For example, there was one law in 1801 which was this coined by this J.C. Proust, and it was called a law of definite proportions. So law of definite proportions. And according to this law of definite proportions, so if we combine two different gases, gas 1, gas 2, together in a container, the resulting gas will be in the gas molecules which are integers actually. So we have an integral number of particles in that gas when we combine those two different gases. This was one that is called law of definite proportion, and those two combining gases, the individual gases.
Repeat, sir. Repeat.
Okay, I will repeat. हाँ बका repeat question. Just wait. Just screen का साथ थोड़ा यार. Okay, no problem. It is here. So what I am saying is that if we have gas A, so we have some, it gives some C here. So this C has a properties which are different from A and B, and this C contains an equal proportion of A and B number, and that too the number of particles will be in terms of the integers. So it was a one, there was a definite proportion of A and B in this C, and the combined gas mixture contains a number of particles or the molecules as integers. So this was one of the concepts from this law. In 1807, John Dalton, he proposed law of multiple proportions, and he combined different gases, number of 1, 2, 3, and in this way he studied actually. There's some problem with the screen. Law of different proportions. And 1808, John Dalton actually he explained by making a hypothesis that elements are composed of discrete atoms. So John Dalton actually in 1808, sorry, screen show hai kya, can you see the screen? So in 1808, Dalton actually he explained by these laws the definite proportion as well as the multiple proportions. He explained actually these laws by making an hypothesis. What was that hypothesis? That the elements, that means obviously gases are formed, the elements are composed of discrete atoms. So for a given element, for a given element, these atoms are all identical. So for a given element, it was proposed by Dalton in 1808 that for a given element, these atoms or the discrete atoms which he called are all identical and each atom has same weight. So Dalton proposed that each atom has same weight. Compounds are formed when atoms of different elements combine in a simple ratio. This was proposed by Dalton at that time in 1800. That means the compounds can be formed when we have two different atoms, different elements, or the different atoms they combine. And according to John Dalton, this they said that okay, this was the what the Dalton actually proposed. At the same time, in 1808, 1800, there was JL guy, and he was the another one chemist which was working at that time. And what he said, he proposed that when two gases combine, थोड़ा सा बोरिंग लग रहा होगा, आई नो दैट इट इज अ थ्योरी क्योंकि ये पूरा थ्योरी है, अभी हम मैन फिजिक्स पे नहीं आए, बट to just give you an idea how atomic structure evolved and how the concept evolved, we will start from the Bohr's theory जो already आप लोगों ने पढ़ा है. This unit is almost what you have already studied. So कुछ concept इसमें ऐसे हैं जो नए होंगे, थोड़े से, ज़्यादा नहीं है, but most of the concepts you have already studied in your BSc classes. So in 1808, according to this chemist, and he supposed that when two gases combine to form a third, the volumes are in the ratio of simple integers, which I already told you that in the earlier classes, in the earlier one. Now, these results actually, the formation of molecules, the mixture of gases, how to measure actually then those gas molecules, how to measure in terms of those integers, or how to measure the gas volume or the weight in terms of the molecules or the atoms which are forming them. In 1811, then results explained by Avogadro. Avogadro. And what he done? He has done that he gave a clear distinction between atoms, which are the discrete particle for element. He termed the atoms as the discrete particle for elements. And molecules, these are the discrete particle for atoms. And the molecules, these are the discrete particle for compounds. They are when they are composed of one or more than two atoms which bind together. And in this way, using this Avogadro's hypothesis, he said that the gas laws they are satisfied at if the volumes are equal. If the volumes are equal and which at same atmospheric pressure. So he said that the gas laws are applicable, or we can say that the gas laws are true when we are we are having the same volume of the gases of different gases and which are at the same pressure. So this was when we reach to the atoms and molecules, how are they reach to this conclusion. So atomic concept from the chemistry side, it was not actually fully explained until late in the 19th century. 19th century means 1890s, 1860s, 1870s. That is late 19th century. That is 1890s to 1900s or 1860s to 1900. That is the late 19th century. So chemists actually they tended to ignore evidence of kinetic theory of gases. They did not go into the details what kinetic theory of gases gives us. So they did not fully explain the structure of atom. In addition to this, kinetic theory of gases actually explained also other phenomena as well. One of them was like important in 1827. That was the Brownian motion, which is nothing actually. It is a collision of molecules. Brownian motion gives us the phenomena in which the molecules of a gas they collide with each other, and when these we suspend some molecules in the fluid, we suspend some molecules or the particles in the fluid. For example, if this is a fluid here, we are suspending some particles in this fluid. So how these particles are colliding with the molecules of this fluid, how these particles which we suspend in the fluid, how they interact with the molecules of the fluid, this was explained by this Brownian motion in 1827. And at the same time, the chemical laws gave us the relative atomic weights of the atoms. Then there was Avogadro number, Avogadro number, and the definition of mole, definition of mole. And Avogadro number was verified actually. It was found experiment how much that means its value was calculated in late 1900, then late years in 1907 actually. During this time, the charge of charge was found. There is some quantity which is called charge. The charge term was coined by actually Faraday, and later in 1833 there was it was argued that it was given that it was proved that the charge is found in discrete units. So charge from the element, charge from the atom. So the charge concept of charge was clear at this time, and it is found in which is called quantization of charge. Quantization of charge. So it was actually at 1833. It was actually already discovered at this point. Later on in 1895, the important experiment of J.J. Thomson. The J.J. Thomson, he discovered that electron, he discovered some charged particle, that means a charged atom contains a negative charge of mass m and charge minus e. That means he found some particle which has a charge m, which has a mass m, and it has a charge of negative e. This was done, this experiment, on the guidelines of the J.J. Thomson by his students, which were J.S. Townsend, and later on they calculated E by m as well, the specific charge, which was experimentally, but the more accurate value, the accurate value of E by m specific charge was found by R.A. Millikan. It was in 1909. late. This was the E by M. This was the more accurate value as compared to the already done. Like there was Thomson's method of E by M, and then the Millikan's oil drop experiment that was also done in this time. This is that. Then we have atom. We are now to the concept that there are some negatively charged particles which were electrons, and then we know their mass as well as charge, their ratio E by M, which just gives an indirect evidence about the value of charge and mass because you cannot find it separately. Then later on, people tried to investigate different phenomena. Phenomena means that they tried to explore more about the atom. How? By performing some basic physical experiments. Like which experiments they were? One was black body radiation. Second, we have the Planck's quantum theory, which explained this actually black body radiation. This is not second actually, this is of this. Then there was a photoelectric effect. Photoelectric effect as well. The Compton effect was there, Compton scattering, X-ray, discovery of X-rays and the X-ray spectra by the Roentgen, those X-rays, and then investigation of that X-ray spectra, how we produce X-ray spectra. So black body radiation actually it was in generally 1870s, late 19th century. So black body radiation. So 1870s. And this gave us the concept of quantization of energy. Quantization of energy means that how they find it is quantized. So the quantization of energy concept and the structure of atom, they are related. As I already in the beginning, I gave you an idea how we can conclude that the levels are quantized energy levels of an atom, or the incoming energy photons, or the energy is quantized, and the basic unit for that is photon. So the spectral distribution actually of the black body radiation, black body spectral distribution of what? Actually those photons which are absorbed by the black body, those, and the best distribution of that spectral distribution of those photons at different temperatures. This study was done actually. The spectral distribution of the photons with temperature, or spectral distribution of the black body with the temperature, it was investigated. And it was later on more explained by from Stephan's law, which you have done in your lab, J. Stephan. And what J. Stephan said that, he said that the power emitted per unit area by a black body, this R, it is
Fourth
actually,
power,
it is,
correctly.
yeah, it is fourth power of temperature. This is the exact expression actually equal to, so it is proportional to T raised power 4. So this temperature and the power which is emitted per unit area, they are related by this law. Then Planck later on stated this black body radiation, since it was not possible to explain this black body radiation from that continuous nature of energy, so the quantization concept came at this time from Planck's quantum theory. And Planck developed his quantum theory in 1900s. So he saw that there are some drawbacks of the classical mechanics which was not able to explain that this black body radiation, photoelectric effect. So Planck devised the quantum theory. And from here, the atomic state or the quantum picture of the atom come into existence using this theory, Planck's theory. So Planck's hypothesis regarding black body radiation was, what he gave about black body radiation was that the energies of oscillator means that if we have a black body, here we have absorbed photons, so these are the oscillators. Actually these photons will act as oscillators which are moving from one end to another end. So the energies of these oscillators, which are actually photons, they give frequency nu. With frequency nu,
With respect to time.
Yeah,
with respect to
can take integral values. So Planck proposed that the spectra, which was of the black body spectra, I think you might have seen it like this in Wien's displacement law. And
yes, sir.
so what Planck proposed that he proposed that the energy of the oscillator, that means that oscillator in the black body, which is actually a photon, and can its frequency nu can take integral values. So that equal to h nu, that nu has some integral values, not fraction, which gave the discrete nature of that radiation incoming in energy. Because incoming energy was coming, the photons were absorbed by that object, by black body. And then later on, another experiment which was done during this time before the Planck's hypothesis was before the Planck's hypothesis. I am saying that it was photoelectric effect. This was first studied by Hertz in 1887, where he found that there's a current if we apply some external light to some metals. And later on, because these experiments were already before the Planck's hypothesis, 1900s, before 1900s. 1900, then when Planck's quantum theory came, it explained most of those experiments. And in 1905, Einstein then explained this photoelectric effect. Photoelectric effect. Yeah, explanation of what for which he got the Nobel Prize actually. And he proposed that Einstein, in his explanation theory, he proposed that the electromagnetic field means the field associated with the photons or any electromagnetic energy source. In itself, it's quantized. And the basic quanta, which is called corpuscles, was a photon, which termed then it was named as a photon, having energy E equal to h nu, where nu is c by lambda. And he also said that the photon it is sufficiently localized, so it does not spread actually in the space. So it is a particle actually. When it does not spread, it's a localized entity. So this was proposed by the Einstein in 1905, and this whole energy, when a photon comes, it strikes some black body, enters into a black body. The whole energy which is associated with the photon is absorbed by the atom at a single time, at once. So the energy comes, it interacts with an atom absorbs all this energy at the same time, which the energy which is associated with the photon. So that means there was some single entity atom inside the object which absorbs that energy at once. And this entire h nu, the energy which is associated by the photon, this h nu, is then ejected in the form of an electron. So this electron here comes of an atom, electron from the atom. And this were then verified by 1914, 1916. This were experiments were verified actually by Milken. These were verified actually at that time. Einstein proposed the explanation actually, and it was verified at later time. Then in later 1923, there was Compton scattering, Compton effect, where elastic scattering, all that has been studied in that. H. Compton in 1923 proposed this, and he studied the energy, radiating
Ah,
energy, the
Jadi
energy
neutral.
atom.
Oh, jadi kan? Rasimal di shahar में राशिमाल di shahar में
And later on, by Rutherford, the nuclear atom. That means this was the outer electronic structure. The structure where with the electrons were found, charge was found, mass, their E by M, then the photoelectric effect, the interaction of the incoming photons with the atom, This has always stated. Then came the nuclear part, which was of course done by the Rutherford, where he found that there is Ze charges, negative charges, then positive charges at the nucleus center, and from that they also calculated the atomic size, and it in 1913 by the alpha scattering experiments. So this is how the atomic structure, the present picture of the atomic structure has evolved from long before. And after this comes the Bohr's theory and the spectra. How then atom will interact with external radiation or the external magnetic fields, external electric fields, external electromagnetic fields, photonic fields, photons. This all we will study in this chapter now. And before that, we will discuss the structure of atom, starting from the Bohr's theory, then Summerfield model, quantization of the energy levels. This all we will now study. So we have reached to a conclusion where we found that there is an atom. An atom has a nuclear part from the Rutherford's alpha scattering experiment. It has a negatively charged electrons which are in the outer shells. These electrons can be ejected by the help of photons when they are absorbed by this atom. By absorption means that that energy is used to excite an electron. By absorption, we mean that the energy is used to excite an electron from one energy level, from the lower energy level to some higher excited energy level. And then what happens exactly after that absorption, if this energy is emitted by the atom in the same amount, or if it is lost some other conclusions, because from the conservation of energy, laws of conservation of energy, that nature will help us to understand the structure of atom. This is all for today. I hope you have been able to understand it.